All right, so let's tackle example 2.27. And this is about finding projections. All right, so let's find the projection of V onto U. So once again, right, the rule that we're going to use here is that the projection of V onto U is equal to the dot product of the two vectors divided by the magnitude of our vector U squared distributed into our vector U. Right, so that's this rule right here, 2.6, that we're using. All right, so for A, we have that our vector V is with components 1, and our vector U has components -1, 4, 3. So I think I'm going to tackle this in steps, actually. I'm going to calculate the dot product first, and then I'll calculate the magnitude of our vector U squared. So U dot V means that I'm taking the product of 3, 5, 1 and -1, 4, 3. Technically, I want to just kind of make a note here. I should have done this the other way around, right? The U goes first. We are conveniently having this property that dot products are commutative, so it doesn't actually matter. But once we get to cross products, it's going to matter. So I want to make sure I'm consistent. Okay, so U dot V. Fantastic. So that's going to be the product of the components all added up. So -1 times 3 plus 4 times 5 plus 3 times 1. 4, -3 plus 20 plus 3, which is 20. Fantastic. Our denominator is the magnitude of U quantity squared. And we know that this is really just the dot product of U with itself. All right, so what we're going to get here then is our components squared, and then we sum them up. So this is 1 plus 16 plus 9, it's going to give us 26. All right, so now let's put it all together. Using the rule that we have, we know then that the projection of V onto U is equal to our coefficient is the dot product divided by the magnitude squared, so 20 over 26, times our vector U. So our vector U is -1, 4, 3. So when I do this distribution in, I notice that this actually simplifies. This is 10 over 13, so I'm going to get -10 over 13, 40 over 13, and then 30 over 13. So this is our projection vector. All right, go ahead and try the next one. So in part B, we're given the standard unit vectors. So our vector V is now in 2 dimensions, 3i minus 2j. And our vector U, also in 2 dimensions, is I plus 6j. So our process is going to be exactly the same, right? We're just interested in the dot product of the two divided by the magnitude of U. So the dot product, U dot V, is, right? This is what we're multiplying. The vector U times the vector V. And once again, we know we're just multiplying the components. So 1 times 3 plus 6 times -2, which is -9. All right. So then the magnitude of our vector U squared is simply the sum of the components of our vector U squared, which is 37. Putting it all together, we get that the projection of V onto U, which is equal to U dot V divided by the magnitude of U squared, distributed into our vector U, is equal to -9 over 37, right? There's our coefficient, times I plus 6j. Putting it all together, we get -9 over 37, I minus 54 over 37, J. go ahead and check our answers. All right. So for part A, it's just a direct substitution, just like we said. They sort of put it all together. That's fine too, whatever method you're more comfortable with. And negative 10 over 13, 40 over 13, and 30 over 13. Fantastic. And then for part B, negative 9 over 37 minus 54 over 37J. Fantastic. All right.